Alright, we're going to get ready to start section 2.5 on rational functions. We studied rational expressions back in the prerequisite chapter. A rational function, of course, as you might guess, would be a function that involves a rational expression. And rational expressions are typically polynomial over polynomial. So here's a nice neat formal definition of a rational function. Let p of x and q of x be polynomials and make sure that q of x cannot be equal to 0. A function defined by f of x equaling p of x over q of x, you can see the rational, the ratio here, the fraction look, is called a rational, let's put that L on rational, a rational function. The domains of rational functions, basically all real numbers excluding anything that makes the denominator 0, so the zeros of q of x, the denominator. So if I said what's the domain of f here, given f of x is equal to 2x minus 1 all over 3x squared minus 4x plus 1, I would first have to find the values that make the denominator 0. So I would set the denominator. I'm not really worried about the numerator being 0. I just can't have the denominator equaling 0 because you can't divide by 0. So we have to exclude those. So I will go ahead and solve this quadratic. This one actually factors, which is always convenient. Looks like a minus 1 and a minus 1. I set this equal to 0. I set this equal to 0. And I get x is equal, add 1 divided by 3, 1/3. Add 1, x is equal to negative or positive 1. Those are the two values that make my denominator 0. So they're excluded from the domain. So if I did the domain of f in the old-fashioned set builder notation, it would be the set of all x such that x cannot equal 1/3 or 1, yet x is an element of the real numbers. So it's all real numbers except for those two guys. Now if I write it in interval notation, which is preferred, the domain of f here would be from negative infinity to 1/3, from 1/3 to 1, and from 1 to infinity. Notice I'm using parentheses here so that I do not include the 1/3 or the 1. Those are the values that make the denominator 0. And this would be how you would write it. Either form here, but this is preferred. Now I have the parent function of the rational functions, which in the textbook is called the reciprocal function, f of x equaling 1 over x. And of course x can't be 0. But what we would be interested in seeing is what happens as we consider x values that are close to 0. Now to get to close to 0, since it can't equal 0, I would either approach 0 from the positive side or I'd approach 0 from the negative side. To indicate that, I'm going to say x is going to approach 0 from the positive side. I put the little plus sign up there like an exponent. What happens to my y value or my f of x value? Well, my f of x value appears to be going up to positive infinity. And that's exactly what's happening. The smaller and positive that x becomes, 1 over x becomes bigger and bigger and bigger. 1 over small is big. So like 1 over 1/10, 1 over 100th, 1 over 1,000, that would be 10, that'd be 100, that'd be 1,000. It's getting bigger and bigger and bigger. So it goes upward and upward and upward. It never touches the y-axis. The y-axis is sometimes referred to as a vertical asymptote. We're going to talk more about that in a minute. Now, as I approach x, or approach 0, my x value is approaching 0 from the left side, from the negative side, which I would write as x approaches 0 from the left side. Then what happens? Well, my y value, my f of x value, appears to be dropping down real fast, and it's approaching negative infinity. So those are, yeah, especially when we get to calculus, because we'll be talking about limits and infinite limits and limits to infinity. This is going to be something that you're going to see again very soon. This is just to give you an overall effect of what's occurring here graphically. Now, end behavior, as x gets bigger, do you see how it's curling out? It's going to get closer and closer and closer to the x-axis, but it's not going to cross the x-axis, because for it to cross the x-axis, that means y would be 0, and y can't be 0 if y is 1 over x, because the numerator is not 0. So as x goes to infinity, my f of x is going to go to 0. And as x goes to negative infinity, so if it goes out this way, do you see how it's approaching 0 on this side? It's approaching the x-axis. So we would say f of x is approaching 0 as well. Now, I have a slightly different function here. I've translated my function because of the -2, 2 units to the right. You see the dotted lines there, they're not actually parts of the graph, so they're just there to help me draw the graph. The graph is kind of in a brown looking color there, and it looks a little bit like this graph, and it should, because this is just a translation. This is a rigid transformation here. It went 2 units to the right. And so now I'm going to use that graph and fill in the blanks, complete the statements here. The graph of f of x equals 1 over x minus 2 is given. Complete the statements. As x goes to negative infinity, as x is going to negative infinity, what's happening to my y? Well, just like over on the other example with the parent graph, it's getting closer and closer to the x-axis, so the y is approaching 0. As x approaches 2, now this means from the left side, so here's 2, 1, 2, right? As it approaches from the left side, you see what's happening to your graph? Your curve is dropping downward, the y values are getting smaller, so f of x is going to negative infinity. Now as x approaches 2 from the right side, as x is approaching 2 from the right side, you see what's happening to my graph? It's curling up, the y values are increasing and going to positive infinity. And as x goes to infinity, end behavior, as this goes further out to the right, you can see what's happening just like on the other end. It's approaching the x-axis and my y value is approaching 0. But what's really nice about this is that you can see 2 key lines that are dotted in red, and they're called asymptotes. This is a vertical asymptote, this is a horizontal asymptote. We're going to discuss both, but I've started out with a definition of what a vertical asymptote is. Now my graph will never cross a vertical asymptote for rational functions. It's possible that it can cross a horizontal asymptote, but it's not possible for it to cross a vertical asymptote because they occur at those values that make the denominator 0, and that can't happen. You can't have 0 in the denominator. A vertical asymptote, the line x equals c, vertical lines, x equals a constant, is a vertical asymptote of a graph of a function f if f of x approaches infinity or negative infinity, like I have here, as x approaches c from either the left side or the right side. And this was from the left, and this was negative, and from the right, and this was positive. That doesn't always happen. It could go to positive infinity as it approaches from the left, or negative infinity as it approaches from the right. This one can't, but other functions can. Vertical asymptotes occur for rational functions at those x values that make the denominator equal to 0, but not the numerator equal to 0. It can't make both. If it makes both of them 0, you don't have a vertical asymptote, you have a hole in your graph. So your graph might be going upward, and then all of a sudden you have a hole in your graph and it continues. And I'll draw an example of that out here for just a second. But let's identify some vertical asymptotes, and I have 4 functions, the last one being from the review. F of x equals 3 over x plus 1. I'm looking at those values that make the denominator equal to 0. Well, the denominator is equal to 0 when x plus 1 is equal to 0, or when x is equal to negative 1. That is my vertical abbreviating asymptote right there, the vertical line, x equals negative 1. Over here, and of course my numerator is constant, so it's never 0. Over here, I'm looking at those values that make my denominator 0, but not my numerator. Now what makes my numerator 0 is negative 7, so I'll have to keep an eye out if negative 7 is one of the values down here that makes this denominator 0. I don't believe it is. So I said 2x squared minus x minus 10 equal to 0. This one will factor, if I'm not mistaken. I need a 5 here, a 2 here. I need it to be minus and plus. So if I set this equal, I'm almost out of space here. So if I set this equal to 0, or x plus 2 equal to 0 here, I add 5 divided by 2, I would get x equals 5 halves. Subtract 2, I would get x equals negative 2. Let's write that a little bit better. I think we can do a little bit better than that, negative 2. And these two guys here are my vertical asymptotes. Now this next one, my denominator is m to the 4th plus 1. Because my variable is raised to an even power, it has a positive coefficient, and I'm adding 1 to it, there's nothing I can plug in that's going to make this equal to 0. Because if I plug in a positive number, positive to the 4th is positive, plus 1 is positive, negative to the 4th power is positive, plus 1 is positive. I can't get 0 out of here, not for a real value, only imaginaries. And I'm not looking at imaginaries, we're doing the real number lines, we're doing the coordinate plane. So in this case, there is no vertical asymptote. Now, I don't mind you abbreviating vertical asymptote as VA because I understand what that is, but if you were in another classroom with a different teacher, I might suggest you write it out. Teacher might not understand. Probably would, but maybe he wouldn't accept it. This last example, which is from the review, I have to look to see what makes my denominator 0. By the way, back here, remember, I couldn't have -7. Well, neither one's -7, so I'm covered. Here, x can't be 1. That makes the denominator 0 because it makes the numerator 0. And you can see it's not going to be. If I set the denominator equal to 0, I'm going to get x equals -3 for my vertical asymptote. And that's not going to make the numerator 0. So we're just starting with the idea of asymptotes. We'll start with a little bit of stuff with vertical asymptotes. We also have to talk about the other two types of asymptotes, which are horizontal and oblique or slant.